Okay, this lecture is on the integrated rate law, which I think is the toughest thing in the whole chapter. And the first thing, I'm just going to take you to this kinetics, and there's these three formulas. I don't use the bottom formula very much, but this formula is for first order kinetics, and this formula is for second order kinetics. And those are the only two you ever have to solve problems with on the AP exam, but they also want you to know about zero order kinetics. And so, and these are called the integrated rate laws. They're different than the rate law because the rate law doesn't have time in it, and it's called the integrated rate law because um, later on, when almost all of my students are finished with calculus or getting ready to be done with calculus, um, you get the integrated rate laws by taking an integral, and the formulas will make sense. But right now, you're just going to use the formula sheet. And so, very quickly, I just want to say that you have first order. Okay, come on, you got to write here now. We have first order kinetics. I always have a little bit of trouble getting used to this thing again. The formula is um, the concentration of the reactant called A at some time. So, like if the concentration at 16 minutes, T is 16, or the concentration at 2 minutes, T is 2. And then this one's my favorite. It's the concentration of A at 0 means in the beginning when time's 0, and this equals negative KT, or the opposite of KT, and it's the same K in the rate law. And basically, first order, this stuff only works for single reactant systems. And so first order, the worksheet that we did the other day, is that the rate for a first order equation is that the rate equals K times the concentration of A to the first. And if you have a first order equation, meaning that's a 1, that's the equation. And then you have a second order, and again, you don't have to memorize these, just remember that they're on your formula sheet and they go in order, and that's the reciprocal of the concentration of A sub T minus the reciprocal. Oh, sorry, this is crazy. I forgot the worst part of this formula. There's a natural log in here. I just did zero order. And then minus the concentration of, the reciprocal of the concentration of A at time 0, or the beginning, or the initial, however you want to say it. And that's equal to positive KT. And again, um, that comes from, if it's second order, the rate law, which is the first thing we do in the chapter. Remember now, this only applies to single reactant systems. K equals A sub 2. Again, I'm going to take you back. You don't have to memorize these. This is the formula for first order. This is the formula for second order. Now, in some applications, this is weird. I don't know why they give it to you, but they also want you to do zeroth order, and I think that is the weirdest word ever. Um, zeroth, and it looks just like first order except for um, the ln. So let me grab this pointer and extend this page. Um, and so zeroth order is you just you take the concentration of A sub T, not the ln, just the plain old concentration, minus the concentration of A sub 0 equals negative KT. And that's what it looks like when the rate is equal to K times A to the 0. But anything to the 0 power is 1. So sometimes they'll write it like that. They don't give you zeroth order, but just know, yeah, I just want to have this sheet up. If you take first order and you just erase these ln's, it's the same. And you don't actually have to solve problems with it, but you have to be able to do something weird with graphs. So it's good to know it even now. Okay, so here's the PowerPoint that I'm going to do, this integrated rate law fixed. And it says at 25 degrees, the rate constant for a first order decomposition of a pesticide is 6.40 times 10 to the negative 3. If the starting concentration is 0.0 0.314 molar. What concentration will remain after 62 seconds? And so an answer is, I put the answer on there. So basically, we got to go back and forth. So here's what we're going to do. Oops, sorry. Let me go back. Most important thing, first order. This term, first order, that's big because that tells you what equation to use. And so I'm going to open a new slide. And what I want you guys to do is, okay, it's first order, so we have to do something with this equation. And the thing about these equations is that they will always give you three of the four variables, and you're looking for the fourth. Now, I just pull this off the sheet. At this point, before I show you the antiderivative stuff, just ln of a sub t minus the ln of a sub 0 equals negative kt. Just take it off the sheet. And this is what we know. The problem says that the rate law constant was 6.40 times 10 to the negative 3 over minutes. Now, the thing about time, integrated rate law, the time can be in seconds, minutes, hours, days, millennium. It just has to be the same. And then the time they're interested in is 62 minutes. And they gave you the initial concentration, which initially is you start the clock at time 0, and that was 0.0314 molar. So let's go back and just make sure that you see where I got those numbers. At 25 degrees, the rate constant for first order decomposition of a pesticide, so the rate constant, which is little k, is equal to this. There's the starting concentration, and we want to know what the concentration will be after 62 minutes. And so if you look at this equation, what we don't know is A at 62 minutes is the unknown. We know this is this, we know the time is this, and we know K is this. And what we don't know is what is the concentration at this arbitrary time, which is 62 minutes. And so now you're going to let the calculator do a lot of the work, because the first thing we got to do is we have to, the rule in chemistry is that you always have to solve the equation for the variable you're looking for. So if you take this equation again, let me switch colors, which is the ln, switch colors, that's red, the ln of A at 62 minutes minus the ln of the concentration of A in the beginning equals negative kt. Well, I'm trying to isolate this guy right here. So the first thing I'm going to do is move this to the other side by adding the ln of A sub 0 to both sides. And then so now I have the ln of A sub t, which t is 62 minutes, equals negative kt plus the ln of A sub 0, and we're almost there. What's the only thing in all of math that undoes a logarithm base? E is an exponential base E. So this is going to be, because the E to the ln, so this is going to give us the concentration at 62 minutes. Sorry, I wrote 6.2. 62 minutes is, and if you do E to the, on this side, you take an exponential base E, you have to do it here. And so extending this page, I think I can do that again. What we're going to do is we're going to take this equation and we're going to go, I think I'm doing purple, there we go. E to the, what's K? Negative. Well, it's the opposite of 6.40 times 10 to the negative 3 over minutes. And then the time is 62 minutes. So the first thing you're going to see is there's no units in here. And then we have to go plus the ln of the initial concentration, which is 0.0314. And at this point, I would just let the calculator do the work. So I have this calculator, and so I'm going to go, oops, this e to the, and then I'm going to put in, I think this is negative. I think I got to do this. 6 point, did the point go? Oops, I can see it up there. 6.40 times, I'll just do this, 10 to the -3, I think it is. Yeah, close that, times 62. And it helps to look up here. Oh, 62, that's 622. 62.0 plus, oops, I'm using my keyboard now, plus the ln, nope, I don't want that. Sorry about this, I'm not so good with this calculator. Okay, backspace, backspace. I need the natural log, which is here, of 0.0134, I believe, and close that, close, oops. And then I have to close that and that. So it's 6.40 times 10 to the -3 times 62 plus the ln of 0.0314. All of that is to the e power, and I'm going to hit equal. And it says that the answer is 0.02111111. And so I would go back to this page and say that it is 0.0211 molar. Sorry, that's a bad looking M. Got to grab my eraser. Sorry about that. Come on, pen me. There we go. And there you go. And if you look at that, that's what the answer is supposed to be. And so if you go back to this equation again, not this calculator, but notice they all have a concentration at some time, and they all have an initial concentration, and they all have a K, and they all have a T. And it's just you take the natural log or the reciprocal, or with the zero order, which you will never have a problem like this, but you might have a graph. All of them have these same 4 variables. It's just sometimes you take the natural log of it, and sometimes you take the reciprocal of it. Okay, so then here's the second problem I like to do. It says the rate law for this reaction is rate equals K times NOBR squared. Now notice this only works for single reactant systems. And then they tell you if the half-life for this reaction is 2 seconds, when the initial concentration is 0.9 molar, calculate the value of K for this reaction. So on this one, what they're giving us is that T is 2 seconds, and that's a half-life. We're going to talk about that means, and that the initial concentration of the reactant, and now this time we're not calling it A, we're calling it NOBR, is 0.900 molar. And they said, and what's the half-life? I need to talk about that, so I'm going to go to this slide. So now I'm doing the second problem, which is, okay, first of all, it is second order, which means we have a different equation. It's not the ln equation, it's 1 over the concentration at some time minus the concentration of A sub 0 equals positive KT. And you won't understand that till I do the derivation, but I just want you to know that you don't have to understand it. This is first order, this is second order. Just use the equation. And then An interesting thing is they're telling us that the initial concentration, I'm calling it A, but A is actually NOBR. So the initial concentration is zero point 0.9 molar. And then we actually know the concentration at 2 seconds because they called it a half-life. And a half-life is the time that it takes for half of this to be gone. And what's half of zero point 0.9 is 0.45. And then the time is 2. So when you have a problem where it says the half-life is 2 seconds, that means it takes 2 seconds for this reaction to be half done. And the reaction is half done because remember now, reactions always start out with 100% A and 0% B, and they end with 0% A and 100% B, and the half-life is when it's 50-50. And so they don't actually have to give you this if they say half-life. Just take your calculator and cut it in half. Now, this is interesting. They want us to solve for K. If you go back and look at the problem, now this is part A. And this happens a lot with half-life problems. First, you have to calculate K. And so the algebra is actually pretty easy here. I'm going to grab this eraser because I don't want to redo all. Oh, sorry. That's supposed to be an eraser. So look at this equation here. I need to solve this equation for K. So all I'm going to do is, pen please, thank you. I am going, still have the eraser, I think. Pen please. All right, so I am going to multiply this side by 1 over t, and then I'm going to multiply this side by 1 over t, and this is going to cancel this, and K is going to be 1 over 2 seconds. You don't really have to carry units on this. Minus 1 over 0.450 times minus 1 over 0.900. And then just let the calculator do the work and keep track of, please excuse my dear Aunt Sally, that you have to do this. You have to type it in like this. An interesting thing to note is, remember, we keep saying that the beginning of the reaction is this is 100% and 0. And at the end, it's going to go 99, 1, 98, 2, and at the end, it's 0, 100%. But the initial concentration is always the bigger number, always, because in the beginning, it's the most A you'll ever have, because as the reaction proceeds, it starts going to B. So what I'm going to do is, now that you have this, because the rule in chemistry is that you, and you don't have to carry units, but I just kind of want to talk about them a little bit. So the interesting thing is that, remember the rule in chemistry is you always do the algebra before you plug the numbers in. So if we go back and go to my calculator this time, what I'm going to type in is, I'm going to hit clear here, hopefully. I'm going to go 1 divided by 2.00 times 1 divided by 0.450 minus 1 divided by 0.900, and then close the parentheses. You can see it up here. So I'm going to do this 1 over A sub t, or A sub 2, because we're at 2 seconds, minus 1 over 0.9 times a half. And if you push equal, you will get this 0.555555. It's 5 ninths. And then if we go back to the problem, it looks like this has 3 sig figs and this has 3 sig figs, and so we probably want 3 sig figs. And it says right here that the answer is 0.556. Just let the calculator do the work. Now, one of the things we talked about when we were doing that rate law reaction is that remember, if it's second order, the units on the rate constant are always one less. So what's one less than second order? First order. And again, the reason for that is, by the way, this is the answer for that problem A. I'm just doing a little aside. If you have a second order, rate equals K times A to the second order. Remember, the units on K are going to be rate divided by A squared. Well, rate is always molarity per second, and then A squared means you'll have molarity written twice. And so it's always the M is downstairs and it's one less than the order number. So what's one less than two? One. And so that's why on this problem I said the units were over molarity to the first times second. Now this is interesting because you have to do this sometimes, because now we're going to go back and do B. How much time is required for the concentration to go from 0.9 to 0.1? And the answer is 16 seconds, I just told you, but here's what you do. Now in this problem, we know, I don't like that, it looks like an eraser. Okay, now we're going to go back to pen, and let's switch to red or black or something. Okay, it's going to look like an eraser. On this one, we know that K is 0.556. We just solved for that in part A. The time is, this is what we're looking for. It says how much time does it take for the initial concentration to go from 0.9 to and T, it really is T, we don't know T this time, to 0.1. And again, it's second order, so the equation is 1 over A sub T minus 1 over A sub 0 equals KT. Well, this time we're solving for T, so I'm going to multiply both sides by 1 over K. And this is 1 over K. And so basically, T is equal to 1 over 0.556 times 1 over 0.1. Now remember, the bigger number is always the initial concentration. And so now we're just going to plug this into the calculator. It's just plug and chug. And so I'm going to hit clear. And this time it's 1 over 0.556 times 1 divided by 0.1 minus 1 divided by 0.9. Close the parentheses and just hit equal. And it says 15.9872 seconds, but if you look at the problem, we get 3 sig figs. And so then the answer to this problem is T equals 16 seconds. They don't make you carry units on this. The only thing is that when you're solving for K, you have to have the right units on. When you're solving for time, notice because of this, time is in seconds. Molarity is always in molarity, and K, you just have to have the right unit on, but you don't have to carry it. All right. Next one in my thing is a certain first order. As soon as they say first order is 25% completed in 37.2 minutes at 25 degrees. First of all, you have to find the rate constant, and then you need to find the value of A. And so here's some interesting things here. It's first order, so the natural log of A sub t minus the natural log of A sub 0 equals negative kt. And in this case, they say, now this is tricky, that the reaction is 25% complete in 37.2 seconds. Let me go back and make sure that I'm not screwing that up. Oops. I need to get down here. Sorry, I didn't mean to make that noise. A certain first order reaction is 25% complete in 37.2 minutes. What is the value of the rate constant? And then what is the half-life? So interesting about this, I just have to tell you some stuff. The first thing is, remember these, it's first order, and in the beginning it's 100% A and 0% B. And when it says 25% complete, this means this is 25%. It's 25% complete. That means it's 75% not complete. Now you can only do what I'm going to show you now for first order because there is a property of logarithms. Let me just go to a new slide and tell you the three properties of logarithms from Algebra 2. First one, the log of anything of x times y equals the log of x, log base b of x, plus the log base b of y. And then the second property of logarithms is that if you have x over y, that's equal to the log base any base of x minus the log base b of y. And then the third property of logarithms is that if you have something like this, the y comes down front, and then this is the log base b of x. And this is the property that you can use on first order. You can use the properties of logarithms on first order reactions. You may not use them on second order because second order reactions don't have a log function in it. They have the reciprocal function in it. And you can't use it on zero order reactions because they don't have a log in them either. And so the crazy thing about kinetics is people try to use you can do that. The subtraction here turns into a division only for first order. And so what happens on this problem, when I erase this, is only for first order. I cannot say that enough. Only for first order. You can rewrite this as the log of the concentration of A sub t minus or divided by A sub 0 using this property of logarithms equals negative kt. And they want to know, I believe we're solving, first of all, what is the value of the rate constant? So we're solving for k, so I'm going to multiply both sides by negative 1 over t. And so negative 1 over t, because negative and negative is positive. Okay, so k ends up being the opposite of the reciprocal of time times the natural log. Now, interesting, if this is, and you can pick numbers, but if it's 75% complete, that means this ratio is 0.75. Okay, let's say this was 1 molar. Now it's 0.75 molar. 0.75 divided by 1 is 0.75. This was 10 molar. This would be 7.5 molar. 7.5 divided by 10. And so basically, this equation, first order kinetics are actually the best kinetics, the easiest to do, because to get k, I'm going to take the opposite of 1 over 37.2 times the ln of 0.75. And now I'm going to go to my calculator and hit clear. And I'm going to go opposite of 1 divided by 37.2 times the ln of 0.7, sorry, going crazy. Gotta go back, 0.75, and then I have to close the parenthesis on the natural log and then close the parenthesis on the multiplication. And then I hit this, and oops, it's not supposed to be negative. So what did, oh, it's up here. It's, no, it's, oh, I know, I didn't put the, let's go back. Anyways, it's 0.00773. And what I did wrong was, let's go back here. I didn't put this negative here when I put it in the calculator. So now if I go back to the calculator, you'll notice that I don't have negative 1 over 37.2 So if I did, this would be 0.00, those don't count as significant, 773. And so when I come back here, K is 0.00773. And now we got to talk about units. It's first order. So rate is equal K A to the 1. What's 1 less than 1? 0. And so the unit is molarity to the 0 times seconds. It's whatever time unit, but that's just 1. So the answer for K is 0.00773 over seconds. You don't have to carry units, but you have to have units on your final answer. So now if you look, that's the answer we're supposed to get. And then the question is, what is the half-life of A? And so very interesting, again, let me do to a new slide. Again, it's the ln of A at some time minus the natural log of the concentration when it started equals negative kT. But now they want to know what the half-life is. So the time for half of this to be gone. And so using the properties of logarithms, again, okay, equals negative kt. Well, now this time we want to solve for time, so I'm going to multiply by negative 1 over k, negative 1 over k, and so what I get is negative 1 over 0.00773, that was our answer for k, times the ln of 0.5, because half-life is when 50% is gone, equals the time. So we want to know the time it takes for the concentration, the original concentration to be cut in half. And so you go back to the calculator, your graphing calculator, or this crazy one I found online that was free. Negative. That's what happened. See, I can't do negative. 1 negative maybe? Okay, divided by. See, it's not negative on here. I don't like this. Let me figure out, divided by, well, now it's gone, 0.00773 times the ln of 0.5, close, and then hit enter. And what comes out is 89.666, so 89.7. So the time it takes to get cut in half is 89.7 seconds. Go back here. This has 3 sig figs. This had 3. And so that's how you do that problem. This one, what is the half-life of a compound if 60% of the sample decomposes in 20 minutes? Assume first order kinetics. So again, this is what I want to talk about here. 60% of the sample has decomposed. So basically, there's weird wording on here that you have to get used to. So now remember, at the beginning of a reaction, it's 100% A and 0% B. And if 60% is gone, that means 40% is left. And so what this question is asking you is the ln of A sub t, because again, it said first order. And most reactions are first order. And the question is using the property of logarithms that you can only use in first order because zero order and second order don't have logarithms. So you can't use properties of logarithms. This is equivalent to this. And the reason why this is important is that this is 0.4 because 40% is left. So this was 100%, this is 40%, 40 over 100 is 0.4. And then they want to know, let me see what we're looking for. What is the half-life if 60% is gone in 20 minutes? Well, this is a little bit trickier because they're telling you that 60% is gone, so 40% is left. And I actually did this bad. I probably should have. Let me erase this. Big eraser. Let's get done fast. No, big eraser, not a pen. Um, so we always want to do the math before we start plugging stuff in. So if I want to solve this, I need to solve this for k first. So I'm going to multiply by negative 1 over t, or the opposite of 1 over t, because then negative, negative, and then t cancels t. So k is equal to negative 1 over 20 minutes. The time unit is minutes. Keep that in mind. Um, times the ln of 0.4. And so you can't get half-life till you first get k. It's kind of like the problem before. And so going to my calculator and hitting clear, I'm going to go 1 negative, how's that go, divided by 20 minutes, and then times the ln of 0.4, and we get that k is equal to 0.0458. So I'm going to come over here. K is equal to 0.0458 over minutes. Why minutes? Because in this problem, the time is given in minutes. And first order, what's 1 less than 1? 0. So molarity is to the 0 power. Now, we're almost there. We know what K is now. Now we want to know what the half-life is. At the half-life, the ratio isn't 0.4. The ratio is 0.5, because half-life is 50-50. So now if I just want to extend this page and, well, let's go to a new page maybe. Okay, so again, we're using the equation with the properties of logarithms. So a sub t divided by a sub 0 instead of subtracting, because the property of logarithms, equals negative kt. But this time we're solving for the half-life. So we're going to multiply by negative 1 over k. And so this gets multiplied by negative 1 over k. And so t is negative 1 over 0.0458. Let me just see if that was our answer over here. 0.0458. And now this time we want to know the half-life. And so it's not the ln of 0.4, it's the ln of 0.5. And so if I go back to my calculator and I hit clear and I go 1 negative divided by 0.0458 parenthesis ln 0.5 this time, close, close, enter, and there's where the 15.1 seconds comes from. And so then t is 15, oh, not seconds, this time the time unit is in minutes. Okay, and the last question, I know this is a long lecture. This 1 second order, see how the exponent is 2? It takes 120 seconds for 1 molar to decrease to 0.2 molar. How much time is necessary for 2.2 molar to decrease to 0.350 molar? So here's the crazy thing. This first sentence, this is the initial concentration. This is the concentration at 120 seconds. You use this first sentence to solve for K. So the time is 120 seconds. The initial concentration is 1, and the concentration at 120 seconds is 0.250. And so the first thing you got to do, and notice it's second order, so we don't use a log, it's 1 over the concentration at the time, which is 120 seconds, minus 1 over a sub 0 equals positive kt. Well, the interesting thing here is we know the time is 120 seconds. We know the initial concentration is 1 molar, and we know the concentration at 120 seconds is 0.25 molar. So now we're going to solve for K first. And the way we do that is we multiply by the reciprocal of T. And just keep track. You got to have those parentheses in there. And so K is equal to 1 over 120 times 1 over 0.250 minus 1 over 1. And I just pop that into the calculator. So I got 1 divided by 120 times 1 divided by 0.250 minus 1 divided by 1 divided by, didn't go, 1.00, and I close that, and I get that K is equal to 0.025. Oh, I remember when I was doing this last year. K is equal to 0.025, but you got to add a 0 because everything is 3 sig figs and that one doesn't count. And the unit is molarity times second. Why? Because it's second order and 1 less than 2 is 1. Okay, now that we know K, then we can do the last part of the problem. How much time is required for the initial, if you do this again with the same chemicals, but it starts at 2.20 and it ends at 0.350, how much time will have elapsed? And so this is my last one. Again, it is second order, so I'm grabbing the second order equation. I don't actually need that parenthesis there yet. So let me just erase that. Now this time they want to know how much time will it take. So we're solving for time. And again, these parentheses are important because now we're going to go 1 over 0.0250. We just solved for that times 1 over. And now remember, the biggest concentration is always the initial concentration. So 2.20 is bigger than 0.350. And so this is what gets popped in, and this is what time is. So the time is, and then finally going back to whatever calculator you're going to use, it's 1 divided by 0.0250, not that you needed that 0, times 1 divided by 2.20 minus 1 divided by 0.350, and it's a math thing, it'll drop those. And I hit equal. Ooh, and interesting. It should not be negative. There is not negative time. Oh, I flipped these. I'm an idiot. If you look here, I had 0.350 and 2.20, but then when I put it in the calculator, I put the, let me just say that again. 0.35 goes first and 2.20 goes second, and I put the 2.20 second. And so this should be, interestingly enough, it's just flipped. This should be 0.350. And this should be the 2.20. Sorry, notice, same answer, just positive this time. So 96.1. So if you go over here, T is 96.1 seconds, which is how much time it would take for. So it's asking you, this starts with 2.2 molar. In the beginning, this is 0 molar. And the question is, when this is 0.35 molar, how much time will have elapsed? All right. 44 minutes. That's even long for me.